We can get started. So hello, everyone. Welcome to the 101 stream and the Intro to zOS session. Our speaker is Steve Warren. And before I hand over to Steve, just a few things. If you have any questions, you can put them into the chat and Steve will answer them after his session. We are recording the session, so you have access to the recording afterwards. And then, of course, we would love to hear your feedback. So here's a QR code to Steve's feedback form. So it would be great if you can fill that out after his session. Right, then, Steve, I would hand over to you.
Okay, thank you, Lena. And good afternoon to everyone. I'd like to welcome you to an Intro to zOS. Now, my name is Steve Warren. I work in IBM Poughkeepsie back in the States. And I love the GSC UK. I've had the privilege of being able to present there for a few years now. And while it's a virtual conference this time, I'm sure that we're going to have a great time this hour talking about an intro to zOS or zOS, as you guys would say over there. I work in the IBM Garage for Systems, which used to be called the Worldwide Client Experience Center, and I'm like a client architect helping clients modernize their architecture in their organizations. I spent the vast majority, however, of my career in zOS development, and so I have a little bit of background in zOS, and so I hope you enjoyed today's session. And like Lena said, please put your questions in the chat, and we'll try to get to it. I normally speak pretty fast, but today we're going to go at full speed because there's just so much material. And when someone says, explain zOS in 1 hour, it's really hard to do that. And so we're going to go really fast. I'm going to talk fast, and hopefully I can pronounce everything very clearly, and that you will be able to ask some questions as you go through the session today. So again, 50,000 foot view. We're not going in anything in very much detail, but we are going to focus on the overall concepts of zOS. Please don't be overwhelmed. This is really just to acquaint you with some of the major concepts. If you don't remember everything that I said, that's perfectly fine. And we'll just take it from there, okay? All right, so we have a lot of topics to cover today, and I'm not going to explain all these topics, but we're going to hit all these major pieces in this next hour, okay? All right, first, just a couple minutes intro of why Z matters. If you're new to the Z platform, you may wonder why we even have a mainframe and why do we have this IBM Z platform. Well, all of these government sectors around the world, whether it's retail, financial, or government, or any of these ones listed here, are all big users of the IBM Z platform. And you'll see in just a moment for good reason. And in terms of how much the Z platform is used, I mean, just think about it. There are 30 billion business transactions every day. That's a B with a billion on the system. 1.3 million KIX transactions every second of every day run on the mainframe. $6 trillion in credit and card payments annually, and 80% roughly of the world's corporate data, sometimes called system of record data, reside on the mainframe. So the mainframe is an integral part of our world infrastructure. But why? Why do they use the mainframe, and why in particular do they use the zOS operating system, the flagship operating system that runs on the mainframe so much? Well, because zOS has a couple benefits that a lot of other platforms don't. It's really ideally suited for processing very large workloads for many concurrent users, thousands of things running sometimes simultaneously on the system at one time. It also has the highest security rating for an OS by several standards organizations. Other folks also, if you look on the internet, you'll find it has the highest reliability rating of any operating system out there. And this is a statement of both the operating system as well as the hardware. It has a low TCO, total cost of ownership, compared to other enterprise competitors, meaning that with the total amount of money it takes to run your data center, including energy, including the cost per transaction, it compares very favorably. And again, it's designed for thousands of users to concurrently. It's great at I/O and numeric intensive computing. And it's great at processing very large heterogeneous workloads, meaning that I have workloads that are maybe dissimilar to one another, and yet they can run in parallel with minimal impact to the other applications that are running on the system. And again, it runs mission critical applications securely. So these are the strengths of the zOS operating system. So with that, we're going to just dive right in and go to our next topic, and the word zOS. And you may have wondered when that came into existence. It's been around since 2001. I'm not huge into nostalgia per se about certain things, but needless to say, you may see these other terms referenced, and in particular, the term MVS, which stands for multiple virtual storage. And MVS is still a term that applies to zOS. It's that MVS refers to the base of the operating system, sometimes known as the BCP of the operating system, the base control program. It's the core of the operating system. And so when you think of MVS, you're going to think of zOS. But zOS, the name has been around for almost 20 years now. Okay. So let's talk about the hardware context just very briefly of zOS. If you're new to the Z platform, this will just be a quick understanding. So first of all, it runs on the IBM Z mainframes, and these are the latest iterations of the latest generation of the mainframe, the IBM Z15. And here we show two different models here that are allowing. Of course, it runs on all of the other Z servers in the past. And so it's just this is just the next evolution in the hardware, the Z15. So if we peel back the onion and look inside these mainframes, we have lots of stuff going on here. But one of the important things is this concept of a logical partition, or an LPAR. And these LPARs are a way of being able to allocate memory, CPU, and I/O resources to a subset of the total capacity of the machine. In other words, I can run multiple copies of operating systems simultaneously on the system, each with different amounts of dedicated resources as of the total pool of the resources in the mainframe for my particular operating system. So in each one of these LPARs, as we call them, you can run different instances of the operating system, and in fact, you can run different operating systems. Okay. We're going to be focusing on the zOS operating system, but there are others that run on the mainframe as well. Linux on Z, ZTPF, VSE, VM, and Linux and zOS can run on top of VM as what we refer to as a second level guest. So if you want, you could have one LPAR that has many zOSs inside the one LPAR, but the most common way in production is you're going to use zOS as a standalone LPAR or many standalone LPARs. So we're going to be focusing on the zOS, the flagship operating system of the IBM Z mainframe. Okay. Let's talk a little bit about how zOS is organized. And so there are the concepts of elements, features, and components. So zOS is a collection of elements. So each element consists of a collection of modules that are called components. So there's a number of components in each zOS element. So I just listed some names of components here. So base elements are always included in zOS. So you have the BCP, like we just mentioned before, the base control program. That's the core of the operating system. That is a base element. You have another component which is going to be accessing the storage on the system. That's called DFP or DFSMS DFP, and other things. For example, communication server allows you to have TCP/IP communication with all of your remote sites and other ZOSs through that, and many other things. Even some compilers are included in the base. So when you order zOS, you get all of those things automatically. On the other hand, there are things called optional features, and optional features are, like we said, optional. So an optional feature can be free. Most of the time, they are a charged extra fee that you pay. Now, some of the things that would be in an optional feature are usually things that of which there is a competition between IBM and maybe another software vendor. So a perfect example of that is the security server. So IBM provides a security server. It's called RACF, and RACF is one of 3 security options that you have on zOS. You can also choose 2 of Broadcom's offerings, ACF2 and Top Secret. So again, you have different options. Of course, we can't include that in the base if there are competitive products, so they're split out and made as optional features. All right, let's talk a little bit about the software stack for just a moment. So how is zOS organized? Well, there's the base operating system, and that's the lower level here that we refer to with zOS, and that is providing the set of critical system services that are made possible by the Z architecture and firmware. And so this is the base operating system that everything else is based on top of. Then you have something that's called the middleware components, which is neither the operating system nor necessarily applications. Usually middleware components you purchase from some software vendor, and that middleware component is going to allow you to provide an infrastructure in many cases for your applications to run. So there are many middleware products that are out there today, and I'll just quickly mention a couple of them. So the flagship relational database on the mainframe is a database called DB2, where there's also Kix transaction server, which provides a framework to run applications very easily on the system, and lots of transactions run inside of that, as well as IMS. You have WebSphere application server. Again, this is the ability to field requests coming in from the net, for example, HTTP requests, and to be able to process them and run the appropriate code on the server to be able to handle those incoming requests. So WebSphere, you have message queuing of things. You even have a couple a product that's not even IBM here was listed, SAP. And then we have TSOE, which we'll talk about in just a moment. So again, these are components, middleware, that is between the operating system and the applications. And then finally, you have applications. Now, there's some applications you could buy from IBM, so maybe like system automation, or even something we'll talk about, ISPF, in a moment. But most of the time when we're referring to applications, it's usually applications that you could have purchased, again, from a vendor, but also homegrown applications that is in your company. So your company has written a whole bunch of applications. They may or may not leverage middleware components, and definitely they're leveraging the operating system underneath. So this is kind of the software stack that we're talking about with zOS. All right, now let's just go a little bit more and talk about how do I write applications on zOS, and where do those applications run, and how do I manage zOS? And let's just talk about that just for a moment. So when you're developing applications on zOS, you have a choice of many programming languages as well as many modern development environments available on the system. So let's just talk a little bit about first languages. So for languages, we actually have a number of languages. First of all, some of the legacy languages that have been around for many, many years. So you have Assembler and COBOL and C, PL1, Fortran. These are the languages that have been supported for a long time, and they still are the languages that a lot of our applications running on the mainframe have been written in. And compilers keep getting updated, and the latest features of the hardware can be exploited, and if you recompile your programs, you're going to get performance benefits. But if you never chose to recompile your program from 30 years ago, it will still run on zOS today, backward compatibility. Then there's the Rex language, which is kind of the de facto scripting language on zOS, and it's a very easy to read, interpreted language that is very simple. And then we have a bunch of modern languages, and these are just some of them, like Java, Python, Node.js, and Scala are just some of the languages that are natively supported on zOS. And so you can write your application in many different languages. So when I'm writing my application in one of these languages, what tooling can I use? Well, if you want, you can use a legacy interface such as a green screen or like an ISPF-based interface. This is what a lot of people think of the mainframe. And certainly there is great support for this environment. So I could write my program in an editor on the green screen and then submit some kind of a job to compile and get that program ready to be executed and deployed on my system. You certainly can do it that way. You also can do it using an IDE environment like an Eclipse-based plugin, for example, IDZ on zOS. And that certainly is a methodology that you can use. And then finally, there are other modern application development tools. So for example, VS Code or Visual Studio Code is a very hot and trendy way of developing applications. And with some configuration, you can actually make this connect directly to your mainframe and to be able to make changes and to be able to deploy your applications just through VS Code. So a lot of functionality available in terms of how you develop your applications. So besides actually writing the code, how can I deploy this code on my system? You have all the tools that are available on the distributed and Linux platforms available on zOS. So whether it's Git or GitHub or Jenkins, Maven, Travis, Docker, IBM Rational, Groovy, all of these things are available on the mainframe as well. So I can have a common CI/CD pipeline for zOS that the same methodologies that I'm using on the distributed, I can have also on the mainframe on zOS. And so all these things are possible on zOS. Now, okay, so I've written my application and I deploy the application, but where actually is that program executing on zOS? There's a number of different execution environments where programs tend to run. First of all, there's traditional zOS application environments, which include middleware. So what do I mean by that? So I might deploy an application to run in Kix. And then it's going to be deployed and run within a Kix region that resides on zOS. Or I might run this as a program, a traditional environment. We'll talk about batch more in a moment, but you could run it as a batch program. All these ways are what we refer to as traditional environments. But we have other places where your applications can run too. So for example, zOS, we'll talk in just a few moments, is a Unix certified operating system as well. So there is a way that you can actually deploy a Unix application very easily. So if you run it under zOS the zOS Unix environment, I could take an application that is Unix compliant on some other platform, bring it over to Z, recompile it so it generates the machine code that Z is going to recognize, and I can run it. And I can run it in the zOS Unix environment. And so that is another application environment that I can run. I also mentioned that you can run Java programs. And of course, there are many languages that are based on top of Java. So Java and all of the languages that are based on Java would run inside a JVM or a Java virtual machine. And so the JVM on zOS is actually very, very good. And so in this case, you could run there. And lastly, but certainly not least, a very recent development, the very latest release of zOS, which is called zOS 2.4. zOS 2.4 supports this thing called zOS container extensions. This allows you to take a Linux application and the exact Linux binaries that run, for example, on a Linux on zLPAR, and to be able to deploy that directly run on zOS directly. So there are some advantages if that application interacts with other zOS applications. So I can actually take a Linux binary, and without any necessary to compile it, I can actually, if it's packaged as a Docker container, I can actually deploy that directly on zOS. So there's all kinds of execution environments that are available on zOS. Again, providing maximum flexibility for you to run varied workloads. And then lastly, we're just now not talking so much about execution environments, but talking about management environments. So you can, of course, manage zOS through the green screen 3270 terminal and to be able to control the functions and operations of zOS that way. You can also use modern tooling such as zOSMF, the zOS Management Facility, which really provides a great modern interface to be able to manage your system through a browser. And so it's a little more intuitive, especially to early tenure folks, to be able to manage the system by utilizing the tooling that's provided in zOSMF. And they keep making tons of improvements to zOSMF to allow more and more management capabilities inside of this platform. So that's all I'm going to talk about in terms of management environments. All right. We've talked a little about some overall concepts. Now we're going to get into a little more detail about the actual operating system and talking about some of the functions that are available here. And we'll talk about some terms. And the first one we're going to talk about is DASD. It's pronounced, this word, and this word, if you're not familiar with mainframes, you will hear people use this term all the time. They do not say DASD, they say DASD. They pronounce it, okay? So DASD stands for Direct Access Storage Device. But again, you're gonna want to say DASD. But DASD is nothing more than the hard drive of the mainframe. The difference between DASD and a regular hard drive is simply the fact that in most machines, whether it's a laptop or a iPad or your phone or whatever, the hard drive is inside of the device that contains the CPU and the memory as well. In the case of zOS, the hard drive is located in a separate box and connected via cabling to the mainframe box. So it's usually a separate standalone device or devices. In most shops, there's many DASD devices that are out there. So there's many hard drives that are outside of the mainframe box itself. Okay, we identify these mainframe boxes by something we call them DASD volumes. So a volume is one of those DASD devices, okay? And every volume needs a label. And so for each DASD device, I have a volume and I have a label which identifies which particular hard disk I'm going to actually be writing to, okay? So there's a 1 to 6 character name that you can represent which disk that your files are going to be stored on, okay? And so just think of that as the vol seer. So remember that terminology. They don't usually say volume serial number. They just call it vol seer, okay? All right, so we have a volume, which one or more volumes, one or more DASD devices that we can store files. Well, in zOS, we call files generally by the term data sets. So, but data set is really nothing more than a file. But the difference between a traditional file that you would have on like Windows or Linux, for example, is that there are many different types that are in different formats on zOS. And in zOS, you cannot just, for a traditional data set, you cannot just write the data set on the fly. You have to do something called pre-allocating the data set. So what that means is to reserve space for that data set prior to the first time you use it. So if I'm going to if I have a place to store my data, I need to first pre-allocate that. It's going to reside on that DASD volume. Okay. So the next thing we're going to talk about is some types of data sets. So there's a data set that's called a physical sequential. Most people just call it sequential data sets. And the idea of a sequential data set is what you would think about when you think about a file on an operating system, right? I open up the file, I can see the entire beginning and end of that data set. Okay, so I can if I'm in editor, I can scroll all the way down and I can see the very end of the data set and the very beginning. It gives you all the data right away. There's also something called a partition data set. And a partition data set is almost, not quite, but it's almost like something that you have like a directory and a number of items inside of a directory, for example, in Windows or Linux. So in a PDS, I create a data set and it has a particular name. But if I go in to edit something in that data set, it's going to have a list of members inside that data set. And when I select one of those members, I only can visualize the data contained in that member. So even though there are many members in this one data set, I can't look at all of the data set. I can only look at the member within the data set. So it's almost like if I'm in a directory in a Unix file system or a Windows file system, and I want to edit a particular file inside there, each one of those particular files in that directory is kind of like a member in that data set. Okay. There's also something called PDSEs, and that can be used usually in place of PDSs. It's the latest iteration of PDSs. The advantage of PDSEs is that you don't have to necessarily modify the characteristics of the data set if you significantly increase the size of the data set. So for example, if I pre-allocate reserve space for X space, and it turns out that, you know what, I thought I was only going to put 10 things inside of this, but you know what, I'm going to put 100 things inside of it instead. Well, you might in a regular PDS run out of room. In the PDSE, the directory can expand to fit all of the members. So you can accommodate having a lot more members, and you don't have to worry about the compression issues. Suffice it to say that compression, all it means is that if I keep editing a PDS time after time after time after time after time, eventually it can start to run out of room because there's wasted space inside of that. I need to compress that data set once in a while. With PDSEs, I don't need to do that. It dynamically takes care of that for me, and many other benefits. So you might heard the term PDSE. I just thought I'd mention it here very briefly. When we talk about data sets, each data set is identified by a data set name or a file name. Okay, so unlike a regular file name that you'd find on other platforms like Linux or Windows, these have a very strict format. First of all, they're not case sensitive. Everything is in uppercase, and each data set name is limited to 44 characters, of which any one part, each one of these segments, which is separated by periods, cannot be more than 8 characters. So fred.assemble.source is the name of a data set, for example. I couldn't have fredassemble source without any dots there. That wouldn't be allowed. So you can each one of these segments between the periods has to be a minimum of 8 characters. Sometimes the first segment is called the high-level qualifier, and you might hear that term being used. If you're creating the data set, typically that could be your user ID, but it doesn't have to be for zOS. So again, this is what we refer to as a data set name. All right, and then we talked about data set allocation briefly, but we'll just touch on it again. The idea of data set allocation is a really foreign concept to people from other platforms. You first create the space for the data set on the disk, and in order to create that, I'm going to need to know what name I want to call it. I need to know what valsir, which of those DASD volumes I want to actually write that data set to, and the attributes associated with that data. Okay, let's talk a little more about when you write data sets and how you can find those data sets. So when I write, let's say I create a data set called fred.assemble.source, and I put that on a particular volume, and let's say we called the volume vol 100. So now this data set is on there. So what we do is on that volume, there's something called a VTOC, called the volume table of contents, and that volume table of contents allows you to find that particular data set. So when I go to that particular volume and I say, give me fredassemble.source, he knows exactly where on the volume that data set is, and he'll give it to you. But that required that you knew the volume name. So what happens? I mean, I'm creating lots of data sets. There's lots of people in my organization that are creating lots of data sets. This could get ugly very quickly. I'm not going to be able to remember where that data set actually is. So to simplify to finding a data set, there's something called a catalog. And you can create a user catalog, for example. And so a user catalog says fred.assemble.source is on volume 100. So I could create a user catalog this onto a user catalog. And what that's going to do is that I can actually now, I know now that fred.assemble.source is on volume 100. I don't necessarily need to know the volume that data set is on vol 100. But the problem is there could be lots of catalogs on your system. So how do we locate the correct one? There's the concept of a master catalog, of which there's only one of them. So the master catalog basically we'll have a definition that says anything that has a prefix of fred.wildcard, anything that has Fred as the first qualifier of that dataset name, go to this user catalog. This user catalog will delineate all those datasets and point to exactly where that is. So now the master catalog is now going to be able to, you're just going to be able to specify the name of the dataset, and the system through the catalogs and the VTOC are going to be able to find that particular dataset. So that's the idea of what a VTOC is and what a catalog is. Okay, as you can imagine, last topic about data and disk, this can get really complicated really fast. And so there's a facility in zOS called SMS, System Managed Storage. And sometimes people refer to that acronym also as the Storage Management Subsystem. Either one is correct. But IBM introduced this concept to be able to address the concern that data set management is very tedious and error prone. And so SMS provides an automated approach to managing all these storage resources. And so what it does, it uses software to manage the security, data placement, and all these other factors. So now let me make you understand. So if I want to allocate a data set, I can use SMS, and SMS will allocate it with the right attributes, put it on the right volume so that all similar types of data sets are grouped on the same volumes, and that it can have management policies of when I move that high performance disk to maybe that data, it's not being used for a long time. I'm going to put it in a place where it takes a little longer to access, but it's going to provide a cheaper cost to my organization. I can also say, you know what, I want all certain types of data to always be encrypted, or certain types of data to always be compressed, etc. And all that can be managed by SMS. So SMS is a huge component of zOS, and I'm talking about it in like 1 or 2 minutes. So the bottom line is there's a lot of functionality with SMS, and that's when you hear SMS manage data sets. It means that SMS is the one allocating and managing the life cycle of that data set. Okay, let's talk about how we interact with zOS a little bit. So first of all, we mentioned that end users, and sometimes tens of thousands of them, may use the system at any one time. So how are we going to be able to manage all of those users running on the system? Well, TSO allows users to log on to the system and interactively share resources. So what TSO is going to do is basically create a unique work area, or we're going to call that, we're going to know that term in a moment, address space, for each user on the system to be able to access data sets and to manage the operating system and to run applications, for example. Okay, so on the green screen, you can log on to TSO. You provide your logon credentials. You end up with a prompt here. You're logged on to the system. It's done a lot of stuff under the covers to create your own space on that machine to execute your programs and or to interact with the operating system. And typically, folks are going to invoke ISPF in this case. So this is something that is of great interest to you. Okay, so now let's talk a little bit about ISPF. So ISPF sits on top of TSO, and ISPF is this idea of a panel application with hierarchical panels. And so why would you use ISPF? Well, you can use ISPF for dataset utilities. You can use it to edit. It has a browser. You can manage the operating system with that. There are other ways of managing it. And some folks who are new to the platform say, oh, do I really have to use the green screen? And the answer is, it depends. You need to be able to know how to use it. There may be cases where you can avoid using it. And so it's important for everyone to at least have a rudimentary understanding of how the ISPF functions work. And so here is an example of an ISPF, and very simple, this is a simple editing. And in this case, I want to specify, I want to look at this particular data set. And so very, 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 very simple type of stuff here. So in this case, I listed a bunch of data sets. And if I want to know what operations I can perform on them, I can just put a slash, and then it lists all the operations I can perform on that data set. For example, editing it. And if I selected edit, now I'm in an ISPF edit session, and I can actually edit my program. I use the function keys to actually navigate in here. And so again, you can write your program. So this is the traditional methodology of interacting with zOS. Now let's talk a little bit about zOS Unix. So we talked about that zOS Unix is a certified Unix operating system by the Open Software Foundation. And this is just another way of interacting with zOS. And you can run Unix applications directly on zOS. So before we talk about the Unix environment, we have to talk about the file system that Unix uses, because Unix doesn't use this idea of what we just talked about, data sets. They have Unix files and in a traditional hierarchical directory. And so in this case, we'll talk a little bit about ZFS. So ZFS has traditional file names. And so when you have a ZFS file, it looks just like any other Unix file. You have a directory structure and you have the name of the file. This name of the entire path, including the file name, can be up to 1,023 characters. Very powerful. And again, like in Unix, the names are case sensitive. Okay. So now, how do I interact with zOS Unix? So how do I access those files, those zOS Unix files that are on the mainframe? Well, there's a number of different ways. First of all, there is the traditional way. If you're familiar with ISPF, you can actually interact with those Unix files using some ISPF utilities. You can access it through something called OMVS, which is a zOS Unix shell, and you can also use remote Unix interfaces. We'll talk briefly about all of them because there are a lot of applications on zOS that have a Unix component to them, or that use the ZFS file system to have Unix files. So let's first talk about it. If you are an ISPF kind of guy and you like ISPF, well, you can actually launch iShell and you can tailor this to your own liking, and you can actually, through slashes and through traditional ISPF interfaces, be able to traverse a Unix file system and then to be able to edit a particular program in ISPF if you wanted to. You can also use the Unix directory list utility. This is 3.17. It's an option on the ISPF panel. You type 3, enter, 17, enter. You get to this panel, and you can then actually be able to look at a particular path. And again, same thing. I can go ahead and edit the file or look at the files and traverse the file system. With OMVS, if you're familiar with Unix shell commands, this may be the way to do. So in this case, as you can see, just up about 5 or 6 lines, you see that there was a CD into the assemble/source directory. So it traverses into that directory. And then I can do an ls, a traditional Unix command, to be able to list the items that are contained in that directory. And then I can, if I want to use still the ISPF editor, to be able to edit a Unix program, I can say edit the program, and then voila, it launches, and then now I have access to the editor there. But many times I don't want to use ISPF. I want to use traditional editors for this, and so there are a number of different ways that I can actually access it remotely. So the first way is through Telnet. So I can actually Telnet to zOS and to be able to edit those either traditional zOS files or zOS Unix files. Probably the most common way of accessing remotely is through something called SSH and OpenSSH. So again, if you generate a public-private key pair that like that you would do normally for SSH, I can actually connect to zOS directly without even providing logon credentials, because I have my private key stored on my machine, right? So again, this is another way of accessing it. By accessing it, this is an example on Windows using PuTTY. I can actually log on. I have a directory structure here, and now I can actually do my things on zOS locally through SSH. I can also use NFS, the network file system, and now the client can see those data sets or files as if they're local resources, when really they're not. But I can actually, I need an NFS client in order to do that. But if I do that, I can actually log in and I can assign, for example, in this case, the J drive. I want to mount the J drive to be a actual traditional data set that's on my system. And now when I do a list of the items on the J drive, this is Windows. So if I did a dir and I hit enter, it's going to give me a list of the members inside a particular data set. So it's very cool. You can access the functionality and zOS files and data sets through a number of different means. Okay. We've talked enough about data interaction. Now we're going to talk about the real core of zOS, the address spaces. zOS is structured around this concept of address spaces. And really what they are ranges of addresses that are in virtual storage. And each user, in the example we just talked about before, gets an address space, which contains the same range of addresses that their program can use to, their user ID can utilize to run programs, to access data, etc. Okay. So again, if I have 3 users here, they all have this address range, in this case, 64-bit address range from 0 to 16 exabytes. That's a lot of virtual storage that is available to your particular application. So besides an address space for each user, of course, zOS is going to create address spaces for some of its internal components. So, for example, a lot of the services on zOS, when you first bring up the zOS operating system, are going to automatically have their own address space as well. And then there's middleware components, and then there's also applications that are each going to have their own address spaces. And there's a lot of those address spaces on the system. And so now let's just talk a little bit about, now that you understand what each address space represents, what makes up an address space inside. So zOS has storage ranges in this address space. And some of that storage range are what we refer to as common storage. Common storage is the concept that every one of the address spaces has access to a particular data area. That data area may be actual executable code in the case of certain of those common areas. Other cases, it may be access to common data that is accessible from any of the address spaces. That's what we refer to as common address space. The rest of the area is referred to as private area storage. Private area storage is the storage in your address space that only you can look at and no one else can unless you give them a special way of looking at it. Okay, so this is the concept of what is called private area storage. So private area, only within my address space I can view it. Common storage, each of the address spaces can view that particular piece of storage, or which may contain programs or data. But how much can your program actually see? Let's talk now about addressing modes. So back in 1977, programs and data were really small. And so each address space was only 16 megabytes. What that means is that would contain, that 16 megabytes was actually not 16 megabytes because there was some common storage which was used by the system for that all programs could utilize. And then I had to put all my programs within that space, and I had to put all my data that I'm accessing from my programs within that space. Not a lot of room, okay? So in 1981, just a few years later, they realized, 24-bit addressing is really not too cool. We need to increase that to much larger. So let's do 31-bit addressing instead of 24. So 31-bit addressing was introduced in 1981, giving you 2 gigabytes address spaces. So this is a significant enhancement. Excuse me. So the concept of the line was introduced. So you hear this concept of the line. So the line was at the 16 megabyte boundary. So what does that mean? Programs that were not changed to support 31-bit addressing had to run and could only access data that was below the line. Okay, so that was that concept. Programs changed to support 31-bit addressing could run above the line. So they could actually be loaded above the line in memory in virtual storage, and they could access data that was above the line. So we need a way to indicate which addressing mode this program supported. So now programs would have to specify when they come up, are you A mode 24, addressing mode 24, or am I addressing mode 31? Meaning that, can my program access data that is above the line, or it can only access data that is below the line? Okay. And again, since A mode 31 programs could run also above or below the line, we had to have a way to request where the actual program can reside. So the A mode is where am I accessing the data? Can I access the data using 31-bit addresses, or should I only use 24-bit addresses? So we have, but now the R mode 24 and 31 is representing where my actual program, the residency of the actual application, is it above the line or is it below the line? And so let's just talk about a couple examples. So if I have a program A mode 24, R mode 24, it means it resides below the line and it's accessing data below the line, no problem. I can also have an A mode 31, R mode 31 program. The program is loaded above the line in that memory space, and it can access data above or below the line, okay, using 31-bit addresses to reference that data in either location. This is also possible. I could have R mode 24, A mode 31. The program resides, I want to be loaded below the line, but it can access data either below or above. But this one is not impossible, is impossible. I can't have something that the R mode is greater than the A mode. And why is that? Because branches within my program, imagine I'm branching to the next instruction. I'm only allowing A mode 24, but my next instruction in my program is actually above the line, requiring more than 24 bits to be able to access it. And so you're not going to be able to even branch to the next line in your program if you were A mode 24 or R mode 31. So this is not possible. All right, moving on to year 2000, we waited quite a few years before we said, 2 gigabytes is really not big enough for an application. Let's move to 64-bit. So they moved to 64-bit in the year 2000 and really opened up the world. And the same concept was used. We'll just go very quickly. We had the concept of the bar, and now we have the line and the bar. And so we're going to have now our A mode and R mode 64. A mode 64 to say I can now access data above the bar. And R mode 64 just starting to come into play now, where sometimes people want their applications actually to be above the bar as well. Okay. The whirlwind continues. Let's go with storage now here. So programs are written to utilize a given amount of memory. They're a certain size, they need a certain amount of memory to load, and they need data buffers in the program to be able to process the data that they need. So as we know, even on my phone here right now, the concept is I could run applications that use far more memory than I actually physically have on that machine. And every operating system has this concept that we need to be able to run a lot of applications, but they are not all loaded into real memory at any one time. This is the concept of what we refer to as virtual storage. So the idea is that I have this massive program that has 16 exabytes worth of data available to me. Of course, I only have a fixed number of gigabytes or terabyte for my particular LPAR that I can actually utilize. And so the bottom line is, when a task is active, it has to go into the real storage. The CPU needs to work with applications that are in real storage, right? So that's what's going to happen when you actually are running your application. But the rest of the programs that are not running at the moment, or that don't have enough priority to be able to run because other programs have a higher priority than them, they can reside in auxiliary storage, enabling the remaining real storage to be used for other programs. So this is how it works. So in Linux and in Windows, they have the idea of what's called a swap disk. In zOS, and I would think zOS's methodologies I think are far superior. It's been around, it's been perfected a lot more, but the concept is very similar with virtual storage. So you have the idea of real storage, virtual storage, and auxiliary storage. So virtual storage is how your program views where the data actually is, but where that data actually is when it's actually running in real storage you don't have to worry about. Your program only deals with virtual addresses, not real storage addresses. And then auxiliary storage, again, where the data is moved off when not needed. And so again, just a couple terms about pages, frames, and slots representing storage chunks in virtual, real, and auxiliary storage. And dynamic address translation is nothing more than the address translation that happens under the covers that converts virtual addresses into real addresses so that your program can actually run in real storage. It's something that just automatically happens in the background. You don't need to worry about it. Let's talk about batch processing a little bit. There's a lot of batch programs that run in zOS, and these workloads are typically run in the background. They don't require much human interaction, and they run as resources permit. So again, these are not programs that you have to run instantaneously. And JCL is the way that's used to control the operations of these jobs. And we'll just talk about that very briefly. This is what JCL looks like. You can think of JCL as very simply, it looks complicated if you've never seen it before. It simply is a way of saying, these are the inputs to my program. This is where my program resides. And these are where the outputs need to go. So inputs, program execution, outputs. That's really, in a nutshell, what JCL does. And you can structure this to have an ordered set of steps that run different programs in sequential order. And again, the // in the first column denotes that it's JCL. So where do these batch programs run? They run in a special address space on the system called an initiator address space. And that's going to process that JCL and basically run that program and set up the environment and actually run that program inside of that address space. Okay. And the management of that job and resources are done by zOS and a component called JES, Job Entry Subsystem on the system. And JES basically is going to manage the priority of all these jobs that were submitted on the system and manage these pool of initiator address spaces and basically manage all your batch workload. And we're not going to go into any details about this, but there's a lot of stuff that JES does under the covers. When you submit the job on the top, it goes through tons of steps before the output is actually done. How do I actually view this? I can use the tooling called SDSF. And SDSF is a neat tool, and I'm just showing you the ISPF interface. There's a zOSMF interface to this as well. But I can actually look at the status of a particular job that I just ran. I can select it, and now I go in it, and I can see several things. This CC, for example, is the condition code. It tells me that if it ran okay or not. Zero return code in batch programs means generally a good thing. You can look at the output. You can see what resources are consumed and a whole lot more in this output of this particular program. You also can use SDSF to look at something called the system log, or sometimes known as syslog. So all this is a chronological listing of all the messages that are occurring on the zOS system. Those messages may be issued by the operating system, by middleware, by applications. The system log also contains commands that you've issued and their responses. So when something doesn't go quite right on your system, you probably want to look at the syslog. And then when you look at the syslog in SDSF, there's usually a message ID on the message. You can actually look up that message and see what actually is going on with your system. Now, when we bring up the system on zOS, let's talk about how we boot the operating system. They call it in zOS terminology IPL. There's always a different name in zOS, right? Other people call booting the operating system. The bottom line is you're starting zOS when you say you're IPLing. So the way you do that traditionally in zOS is to go onto this special console connected to the internal network of all your mainframe boxes. It's called the HMC, the Hardware Management Console. And you're going to activate a load profile, and you're going to load the operating system into this LPAR. So you have an LPAR, a logical partition, and I'm going to say for this LPAR, I want to actually run it. So here's a list of LPARs in the Hardware Management Console. I'm going to click on which LPAR I want, and I can click on the load operation below, and it's going to load the operating system. It's going to prompt you for a bunch of things. The most important thing is the load address. This is going to say, where does the zOS instance that you wish to IPL, wish to boot, reside? Which of those DASD volumes that I have out there, which device number contains that particular zOS operating system. So you're gonna load the operating system, and then the operating system starts booting up. And there's a lot of different things that can happen, and we're just going to quickly go through some of these. The first thing is when you boot the operating system, you specify again the DASD where the zOS is. It's going to start the bootstrap program for zOS on that volume. And then you're going to go through a number of phases. We're going to skip over a few of them and go right to this phase called MSI, Master Scheduler Initialization. And Master Scheduler Initialization will start several major key components like SMF. SMF is a reporting mechanism on zOS that is going to allow you to evaluate what's going on the system, what's the performance, what system resources are being consumed, and even for billing purposes. There's System Logger, which allows you to merge logs between multiple systems. There's BCPII, which has a special APIs that you can use from a zOS application to actually talk to the hardware. Once you get past MSI phase, the last major phase of the zOS operating system starts all of the started programs, and you can have a startup configuration member that will allow you to actually tell the operating system what programs you want to start. Of course, people are going to want to start JES very early. You can start your security product, for example, RACF, your crypto products that manage the keys, digital signatures, and interact with the cryptographical hardware on zOS. And you can store several communications things such as TCP/IP to actually enable that functionality. At this point, if all those things come up, the operating system is considered complete, but that's just the beginning, right? When you're IPLing, of course, there's a lot more work to be done. You have all those middleware components. So if you have Kix and DB2 and all these other things, they need to come up. And then finally, your applications need to come up. And then once all those things are up, now you have a system that's ready to process incoming work from the outside world. Let's talk briefly about Sysplex. So Sysplex is a way of providing higher availability. Now, everyone is familiar with the concept of containers. It seems like that is one of the most well-known technologies in recent years, and Red Hat OpenShift and Kubernetes and all that stuff. So that is kind of like almost like a duplication of what Parallel Sysplex is. But Parallel Sysplex is really a state-of-the-art technology. It's a way of treating multiple systems and viewing them as a single very large image. And this is done for availability purposes, right? So that I don't have a single point of failure. So a Sysplex is a technology that allows a bunch of zOS systems to coordinate and cooperate with one another. And in many cases, if it's a parallel Sysplex, that uses multi-system data sharing. And again, we can distribute that workload to many systems on the Sysplex, and it can be even distributed based on the processor capacity of that system and the priorities of the systems. So again, to provide higher availability. So in this example, I have two mainframes, and they're both in the same Sysplex, one on each different mainframe box, or CPC. The mainframe boxes are called CPCs. So there's a couple components that help manage the Sysplex. They are XCF and XCS. So XCF is the communication mechanism, is the guide that manages the communication mechanisms between the different systems in the Sysplex. And so each system can communicate with one another using signaling paths. XCS manages the ways of taking advantage of this common shared storage that is in the coupling facility. And coupling facility is data sharing across systems in the Sysplex, and it's all synchronized, and multiple systems can write to the coupling facility at the same time, and it'll all be synchronized. In order to have multiple systems and multiple mainframe boxes all in the same Sysplex, I need to have a common time reference. In other words, they all have to have the exact same time. Because I'm running transactions so quickly, even off by hundreds or thousands of a second can be a earth-shattering and unacceptable thing. Think of stock trades, and which one gets in first. They all have to have the same time stamp on all the systems. So there's STP, which helps synchronize the clocks. And then we have the idea of finally coupled data sets, which manages the configuration of the Sysplex. It's a shared DASD that actually contains the configuration and status information for the Sysplex. Okay, we're going to go over by about 5 minutes. And so I would ask you to be patient with me. We're almost done. And so if you just can wait 5 minutes, we'll wrap up everything, okay? So now I have this XCF, which allows communication between the two systems. I have XCS in conjunction with the coupling facility, allows me to share data between those systems in a very fast and robust manner using shared memory. So in this case, applications now that are written to take advantage of parallel Sysplex that can have multiple instances of their application running on all the systems in the Sysplex or some of the systems in the Sysplex. And I now have easy data access from all the images. And I have high availability. When one system goes down, this is a really dumb example. I only have 2 systems in the Sysplex. So if one goes down, I have 1 system left. In reality, you might have 4 or 5 systems in the Sysplex. And if one goes down, the other 4 are just going to take over the workload that maybe the 5th one would be doing. If you had to, for example, had an outage, or if you had a plan outage, you want to apply maintenance on that one system, the other guys can take over the work temporarily while and still have 100% availability of that application. All right, 2 last topics, serialization and managing workloads. So serialization, we talked about zOS running tens of thousands of transactions per second on some clients literally have that kind of workloads that run on the system. With many concurrent programs and many threads of the same program running simultaneously, think of credit card transactions, for example, there has to be a way of managing updates of resources at the same time. If I have 2 people, a husband and wife, each making a purchase in a different store at the exact same moment in time, and they each have to do a credit check to see what the balance is, you need to make sure that you only allow one to look at it at a time. Otherwise, you may extend too much credit to them because it looks like they have enough balance, but after one person makes the purchase, now they wouldn't have enough balance for the second person. So of course, we have to be able to synchronize and serialize resources. And that could be, the resources could be data sets. It could be virtual resources like lists, queues, or data areas, for example. And so how do we ensure data integrity and fair access? Fair access meaning simply that we make sure that the first person comes in is going to have the first access to it, the second person is going to have the second access to it, et cetera. All this is managed through something called GRS, Global Resource Serialization, and it protects the integrity of the resources in this incredibly multitasking and multi-host environment. So it coordinates the access to the resources, and it uses 2 concepts, enqueues and latches, to actually make that happen. And they can have various scopes. So I can scope things at within a single address space or even across an entire Sysplex about my how the serialization is held. So if one system comes in, one request comes in from one member of the Sysplex and another one comes in from another member of the Sysplex, I can make sure that they are serialized even in that example. And so the program obtains these enqueues or latches before they read or update the protected resource. And they say, do I need exclusive access? Do I want to lock everyone else out from getting access to this guy? Or can you have read access? I'll let everyone read it, but no one can update it because I'm reading it right now. Don't update it under the covers for me. Last topic, managing workloads. So I consider this to be one of the real signature items of zOS, the ability to run multiple workloads at the same time within one zOS image or across multiple images. And the fact that zOS has the abilities to prioritize this work and use the installation resources as efficiently as possible and maintain the highest throughput and obtain the absolute possible best system responsiveness. And the magical component that makes all that happen is something called workload management, or as most people refer to it as WLM. And WLM allows you to define performance goals. You can assign a business importance to it. And so I can actually now say how much CPU and storage should be given in order to meet a particular goal. So if my system is 100% busy, who am I going to give the resources to, and who am I going to make wait a little bit because they're not quite as important as someone else. Okay, and again, WLM has algorithms that periodically are going to adjust the allocation of these resources as your workload changes, and it's really a powerful tool. And it coordinates and shares performance information across the Sysplex even. It can dynamically start and stop address spaces. And finally, it collects real-time performance data and delay monitoring. All right. Now that your head is spinning and the birds are chirping and going in a circle over your head, after all that stuff, I know I told you it was going to be a whirlwind. I just want to tell you that I thank you for your time. Are there any questions that you may have? I know we're 5 minutes over. I apologize for that. But what questions do you have?
Thank you very much, Steve. I'm just looking in the chat. I don't see any question there so far.
Okay, so I would encourage you to look at the material that I sent you in a little more detail. My information is available. You can contact me at any time. My email address is swarren, SWARREN @us.ibm.com. I'm more than happy to explain any of these concepts in a lot more detail. This session normally is a 3-parter for 3 hours. And even then I'm going pretty fast, and I tried to condense it down into 1 hour. I guess it was 1 hour and 5 minutes. And so it really is a fire hose worth of material. But the goal of this session is to at least introduce you to what zOS is and some of the concepts that are available. So we would encourage you to fill out a session evaluation to let us know how we're doing for the conference. And you can scan this QR code to help facilitate that and make it easier if you'd like.
Thank you very much, Steve. And just we just received one question regarding the recording. So yeah, the recording will be shared afterwards. And you get some very, very positive feedback. It was a very useful session.
Okay. Okay. Well, I appreciate it. And you can also be honest with you if you really found that it was absolutely too fast. We'd like to take that under advisement, but we'd also like to, you're both positive and constructive criticism. So thank you very much for your time. I look forward to speaking with many of you throughout this week and the next week. I'm presenting 3 sessions next week for the GSE, and always love this conference. I love the energy that is in the face-to-face event in particular that is there, and looking forward to hopefully being face-to-face with you guys next year. Cross our fingers. So
yeah. All right, and thank you everyone for joining.